One, go.
Okay, so we are Group One, and we're designing a conventional water plant in Chicago called the Chicago Water Plant. My name is Noah Zapata O'Brien.
My name is Yerima Sandoval.
My name is Christian Talavera.
My name is Maria Nelson.
My name is Brixie Guzman.
Okay, so getting into this project, first we are going to have the overview where we are going to look over the plans for the site.
So first, we're going to discuss our site location. The site that we chose was located within the city of Chicago. The project site is located at Lincoln Park at 500 to 5,700 North Lakeshore Drive in Chicago, Illinois. It's right next to the Lake Michigan, which will be our source of water for the plant. The elevation is higher for the site, so we do need pumping in place in order to retrieve the water from Lake Michigan. They will support approximately 125 million gallons per day as our Qmax, as this must meet the demands for population of Chicago within 20 years. Our surface water quality. So these are some of the parameters that we took into account. These are the maximum contaminant levels and maximum contaminant level goals. Some examples of these are barium, copper, lead, fluoride, nitrate, radium, total coliform, fecal coliform, turbidity, and turbidity for highest single.
So this is a flow diagram of a conventional water treatment plant, which begins with the source, following flocculation, coagulation, flocculation, sedimentation, filtration, disinfection, clear out, and then out to the city distribution, which we will be going further into depth in the design. This is also another just schematic showing the coagulation, flocculation, sedimentation, filtration, and clear out.
So what we're looking at here is the coagulation design. The purpose of the coagulation tank is to allow the addition of the coagulants so that it can be ready for the next stage of treatment where it aggregates into larger particles. But this is the section where that precedes that section. And you see the dimensions of the tank. We have two tanks. The detention time is 30 seconds. The height of the tank is 20 feet. The diameter is 11 feet. And the total volume of the tank is close to 2,000 cubic feet.
So as previously stated, for the coagulation process, we need to make sure that all our coagulants mix rapidly and to form little small flocks. So in order to do that, we have to use a 54-inch diameter four-blade impeller because this is what works with our design due to the fact that we use geometric ratios to decide that. And then as well as that, we also need a general motor in order to power the impeller. And for that, we chose a North American Electric model PE326TS with a max horsepower of 50. And this will ensure that we have proper function for the coagulation process.
So going into flocculation, the purpose of the flocculation tank is to for the aggregation of the large particles to precipitate down due to gravity, as to why we need a detention time of 40 minutes. There will be 6 tanks and a water depth of 15 feet, a length of 60 feet. The tank height would be 17 feet, and the tank water volume would be close to 50,000 cubic feet, and the total tank volume would be 5,600,000 feet cubed, sorry.
So for flocculation, since it is a slower mixing process, the impeller chosen is the 60-inch diameter four-blade axial flow turbine. For this, he approximated cost estimate per impeller was 4,562, which brought it up to a total of 27,372. And then for the motor, each motor would be approximately $2,500. And for the motor chosen, it was the North American Electric model with a max HP of 15, which is significantly lower than the HP required for the coagulation motor.
So going into sedimentation, the purpose of this is to remove the flocks from the influent through precipitation. The different types of particles that it removes, it's colloidal particles, discrete particles, as well as which consist of silt, gravel, and sand. This has a higher detention time, which is 2 hours. We will have a number of 8 tanks, which consist of a width of 42 feet, a tank length of 208 feet, a water depth of 13, as well as a tank height of 15. And listed there are some other parameters such as the surface overflow rate, the weir loading rate, the tank volume, as well as the horizontal velocity. There will be 4 launders, and the length will be 70 feet, and the weir length would be 555 feet. Moving on to filtration, the purpose of filtration is to remove suspended solids from the water by allowing it to flow through porous media, which will then absorb and retain solids through common methods. And here we have 10 filters, which will have a length of 54 feet, as well as a width of 18 feet. And for the filter media, we will have dual media, which would consist of anthracite and sand. The filter media depth is 6 inches for the anthracite, and then for the sand will be 24 inches. Kind of just going into more parameters on the filtration rate, the backwash rate. Filtration rate would be 6 gallons per minute feet squared. The backwash rate would be 20 gallons per minute per feet squared. The backwash flow would be 1.4 gallons per minute feet squared. And the backwash will last 20 minutes. The surface wash water flow rate is 1.3 gallons per minute feet squared, sorry, and then this will last 6 minutes, and the total wash water will be 1.24% of the plant flow, and the filter trough length is 18 feet.
So for our filtration system, we needed to implement a sludge collection and pump in order to get all the sludge out of that system. And for that, we used the parameters given, which was to use 80% efficiency, have a 60-foot head, and we had to have 1 sludge or pump per tank. And we used all these factors to choose a KZN55CH solids handling pump. This pump is ideal for removing solids from any water system. And as well as that, we also use a NCS-720-S chain of flight collector system in order to move the sludge out of the system and release it outwards. Next slide.
So the clear well follows the sludge collection process, and that's where the polished water goes following treatment. And it also allows the chlorine to come into contact with the water for disinfection purposes. It also stores the water for backwash cycle when that needs to happen. So we have 2 tanks. The diameter of each tank is 120 feet. The height of the water is 30 feet, and the freeboard is 2 feet. The detention time is 12 hours. And then following this, it goes out to distribution. Did your head sing the whole?
Okay, so getting into our chlorine system. So chlorine is an essential chemical in the water treatment process. It is actually used several times throughout the plant, and it is very important because it kills bacteria, viruses, pathogens, and microorganisms. One of the most important times that chlorine is dosed into the system is right before it goes to the distribution system. That way, when the water is in the pipes, these pathogens and microorganisms cannot regrow as it is getting distributed to taps. Some important things about chlorine. The dosage of chlorine does change as the water quality changes, as well as also as the plant flow changes. So as you can see here, we do have a minimum plant flow of 12.5 mgd, but a maximum plant flow of 125 mgd, with the average plant flow being around 50 mgd. So as that changes, the dosage is going to change as well. So our minimum dosage is 1 milligram per liter, average dosage of 3 milligrams per liter, and then a maximum dosage of 5 milligrams per liter. For our chlorine total, there is a lot being distributed throughout the plant, as I just mentioned. So we do need to have on-site chlorine storage that meets the demands of this plant. We're able to find that by taking the dosage times the plant flow and then multiplying that by the storage in amount of days. So we did find that we would need a chlorine tank of 16 tons, which means that it is holding 16 tons of gaseous chlorine, and we would only need one tank to hold that amount. We are thinking that the tank is going to need to be built, as tonnage tanks that big are not readily available. Next slide. Getting into chemical facilities, so there are two other chemicals that we do need to worry about. Those are going to be alum and polymer. These chemicals are necessary for the coagulation and flocculation process, as they help suspended particles clump together. And once again, we do need to have a certain amount of them on site in order to be readily available for these processes. So our givens were that we had an alum dosage of 14 milligrams per liter. We're using 50% liquid alum solution, which is 5.4 pounds per gallon. And then the alum storage that we need to have ready is going to be 60 days worth, as well as being held in 2 tanks. For our polymer dosage, we're looking at 0.5 milligrams per liter, 100% solution, which is 8.4 pounds per gallon, and then a storage of 60 days over 2 polymer tanks. So for our alum tank size, we were able to calculate that we would need a quantity of alum of 64,867 gallons, which means that we are looking at, since we are looking at 2 alum tanks, we are suspecting that we would need 2 35,000 gallon tanks to hold the 64,000 gallons of alum. And then for our polymer tanks, we would need significantly less, calculating that we only need a total of 1489 gallons over the 60 days. And then once again, with 2 tanks, we would be dividing that into 2 750 gallon tanks for 1,500 gallon storage total. Next slide.
So next we discuss the raw water and intake pump station. Like we said before, there is a change elevation between our water source and the site, so there was pumping required. The purpose of the pump stations within the wastewater treatment is to convey the water, of course, from lower to higher elevations, so we can get the water to the treatment plant. So we designed for a total of 6 pumps in order to minimize the flow capacity per pump, resulting in 32.2 cubic feet squared per second per pump. And the static head determined from the elevation difference was 36 feet, and the friction head determined using the Hayes and Williams equation was 2.09 feet. This is the equation used for total dynamic head, and it was static head plus 4.727 times the length of the force main and times the Q max to the power of 1.8 over the diameter that we determined for the pipes to the 4.8 power times the C value, which we determined to be 140.
So for our pump station, we decided to go with S series end suction standard centrifugal pump from Pioneer Pumps. And as you can see, this table above gives the design requirements that we came up with, which is about like 15,936 GPM. We needed to have about 140 horsepower, and we had a total dynamic head of 38.09 feet. So the pump that we actually found compensates for all that pretty well. because the max flow for our pump that it can take, it would be 18,000 GPM. The max horsepower for our pump is 250 horsepower. And the max head that our pump can withstand is 210 feet. And as you can see here, here's our pump curve that we got from the manufacturer. And this pump curve, what it tells us is how efficiently our pump is actually going to work, given our parameters, given our constraints, how efficiently it's going to work throughout throughout the cycle that it's going to be on for. And yeah, next slide.
Okay, getting into our hydraulic profile. So as we said before, our source water is going to be Lake Michigan. That sits at an elevation of 575 feet. From there, it is going to be getting pumped up to our plant, which is only a short distance away. Is going to be pumped to the highest point on the plant, which is going to be the rapid mix at 611 feet. I believe the highest point on our site was around that. There would have to be some grading done. From there, it is just a short drop to flocculation, and then another short drop to sedimentation, taking us to 607 feet of elevation. A slightly bigger drop of 5 feet to filtration, and then our biggest drop in hydraulic head from filtration to the clear well, as there is a good amount of water head needed in order to get through the filtration process, as well as the fact that our filtration process is just going to be a rather deep drop, as we drop from 602 feet of elevation in the filtration to an ending height of 588 feet of elevation in the clear well. Next slide.
So for our cost estimate, we decided to use the following curves in order to determine how much our project would be costing us over time and give us our total. So the way we actually got these curves were from the Engineering News Records Index, which is an online source that gives us predetermined models that have been taken over different cities, over different years, over different periods of time, that all give us like these regression models. And from the regression models, we get these equations that we can use to actually determine our costs given the quantities that we're going to use for our site. Next slide. And here, as you can see, are all the equations retrieved from those regression models. And as you can see, the total cost for our project is going to total about 224 million dollars. And with all that, we included, just general things that are going to be expected, such as administration, laboratory costs, operations and maintenance, construction costs, as well as, yard piping, landscaping, electrical and controls, and just other typical things that are going to be within our site. Next slide. And so here are references for the project. And thank you for listening.